Welcome back. In this final video of this week 9 of inverse methods in heat transfer, I want to give you a brief argument for why neural networks are required. We already saw that a simple network such as this is capable of doing linear regression. So that's a regression task. And a simple network like this with just a summation and a sigmoid is able to do classification. Even for multi-class classification, we just need to add more neurons here. So why these neural networks? More specifically, a neural network is exactly this kind of network, except it has more layers in the middle. So you have these intermediate calculations. So suppose you are actually doing a true multi-class problem, the cat, dog, horse, the problem that I talked about, the output would be after a few hidden layers. What these hidden layers are, I already explained once, but I will also show it to you in greater detail in the next week's video. But you see, at the end of it, it is just neurons connected to each other. Okay, so I am not drawing a fully connected layer here, but you can imagine that we have these multiple connections throughout between input and output. Now, why these hidden layers? What exactly is the need for this? So I'll briefly argue about this. There is a longer argument to be made here. I can make a more precise argument. But considering time and also the focus of this course, which is not really on neural networks per se, but on for you to gain some intuition about new inverse methods, I'm going to give you only a simple argument from the OR gate example that I showed. So remember the OR gate example that we had this simple data set. 3 of the points classified in one way and 1 of the point classified in another way. Now, of course, this is a simplification of actual data, which might look like this. It might cluster more like this with a few unknown points here. Okay, so this might be the actual data. What we saw was in all cases where we had y hat equal to sigmoid of z, and where z was a linear combination of all the x's, the classification was via a line, z equal to 0. So it was always a straight line, which represented w0 plus w1 x1 plus w2 x2 equal to 0. Now you might remember, again, if you don't, please do take me on trust. You might remember from 3-dimensional geometry that this actually is the equation of a line. And if I put w3 x3 equal to 0, that would be the equation of a plane in basically 3D. But in all cases, it's a straight line. Now, how is this a problem? The problem is that logistic regression or even multi-class classification, the way we showed it, works only for linearly separable data. Okay, I'm going to qualify this shortly, but only linearly separable. What does linearly separable mean? It means if you look at these two sets of points, you can actually draw a line in the middle and separate them. What would be the example of something that's not linearly separable? So there is a famous historical example called the XOR gate. So you could have data of this sort. Now see, there is no line. If I draw a line here, I get one wrong. Not only do I get one wrong, well, occasionally while classification, it's okay to get a few classifications wrong. Okay, so you might have some data spread like this. But this is an entirely different beast because remember, this actually represents something a little bit deeper. Okay, so if you have data of this sort, you have to get a lot of points wrong. In fact, you will get entire clusters wrong if you just draw any separating line at all. So if I draw a separating line this way, it would be wrong. This way, all of these would be equally wrong. Let me show another data set which is not linearly separable. And that could be some data set like this. Some set of points here and another set of points outside. Okay. Now you might say that, okay, it's not a line, but at least a curved line will work, maybe a circle. Let's say this is the variable x1 and this is the variable x2, x1, x2. Similarly, you could think of a classifying curve like this. But the equation would no longer be z equal to 0. In fact, this one we can say something like, let's say, assuming this is a circle, obviously it's not a circle, but let's say it's a circle, you could have something like x1 square plus x2 square plus 2x1 plus 6x2 plus 12 equal to 0, or x1 minus some constant square plus x2 minus some constant square equal to some r square. So this curve could be a curve like that. But notice this is no longer linear in x1 and x2. In fact, if I have to add neurons here, just like we were doing with linear regression in the earlier weeks, I will explicitly have to add x1 square, x2 square, something like x1, x2. So this leads to more non-linear features. Again, this might not seem like a serious problem. So what we have decided so far is that in case you want to use pure logistic regression with just x1, x2, it will only give lines. Why will it give only lines? Because the line is z equal to 0 and z is always w1 x1 plus w2 x2. If you want w1 x1 square, you have to add that. Okay. And if we add that, we get more features. Now notice, if I want a quadratic curve, I have to add 3 more. If you just have 2. Now, if it was x1, x2, x3, you will have to add x1 square, x2 square, x3 square, x1, x2, x2, x3, x3, x1. Now, if I have to add cube, then of course it's a whole lot more. x1 cube, x2 cube, x3 cube, x1 square, x2, etc., etc. This leads to an explosion in non-linear features. This is called, in machine learning, the curse of dimensionality. The idea being that the more features you add, it is not possible for you to just get rid of it by just putting something like this simple case. What is simple about this? You had one input and direct output. So curse of dimensionality has a problem when input directly relates to output. This will require lots of features. On the other hand, it turns out that if you add hidden layers, in fact, even one hidden layer, and you keep it arbitrary. So I have, let's say, x1, x2, and this 1. And I add a huge hidden layer here. We don't know what it means, and then give an output. That you have access to what is known as the universal approximation theorem. The universal approximation theorem says that all your computation load of adding lots of layers here, you can dump them here, provided there is a sigmoid or other non-linearities, which I'll talk about in the next week. So provided you add one hidden layer with a sufficient number of neurons, you can actually, with without extra computation, or sorry, without extra features here, you don't need any extra features here. Universal approximation theorem says you can approximate any function to any accuracy. Now, this looks too good to be true, but it is true in that you can approximate any function to any accuracy, provided you are free to choose a lot of neurons. Now, you don't explicitly have to provide x1 square, x2 square, which is operating on the data set. You just keep on increasing this number of layers. And this computation basically takes care of having approximating your function. The disadvantage, of course, is that you have to add a lot of weights. But we are happy with that because that computation is a little bit easier to do rather than actually calculate arbitrary functions of our input. So what we saw in this video is that logistic regression will do only linearly separable tasks. For more arbitrary tasks, it makes sense to include intermediate calculations. And how to do these intermediate calculations and how to find the gradients and how a neural network works like this, we will see in the next week. And the next week, you will see how we can also directly apply what all we have seen to inverse problems in heat transfer. So I'll see you in the next week. Thank you.